Hello students, welcome to the session here and case 3. Now this is the case 2, right? We have seen case 2 actually. Please write it here. The load is the voltage source, right? In the earlier case. We have drawn here but we have not written here, right? So load is voltage source. Okay, but this is variable. Always the load must be variable. Case 3. Case 3. Case 3. Load is current source. That is nothing but what? IL here, okay? IL. Now, see, load is nothing but what? It should absorb the power, right? So now current source is said to be absorbing power only when that current is entering into the positive terminal. That is why IL, and I am taking the downward direction intentionally. This is what variable. This is RTH and this is VTH. Okay. The current source IL and VL. Okay. PL is equal to VL into IL. Okay. Here VL and IL in this, again there are two variables. PL is equal to VL into IL. When IL is changing, what is happening? VL will also change. Simple, because when IL is changing, the drop across the RTH will change. VTH minus the drop is nothing but VL. Therefore, when IL is changing, VL will also change. Yes or no? That is why we try to express now this VL in terms of IL and other constants. That's it. So what does that tell me? VL is nothing but VTH minus RTH into IL. Okay. Now, see this entire equation is in terms of VTH constant, RTH constant, IL and IL only one variable. So let me just take DIL. Yes or no? Is equal to 0. Now what will happen? VTH into IL. You get VTH when you differentiate. IL square into RTH. 2 times RTH into what? IL. Yes or no? Then what do you get here? IL is equal to VTH by 2 times RTH. This is what condition for maximum power transfer. Now you substitute the same thing in this equation 1, Nana. Equation 1. You call it 2. Okay? When you substitute equation 2, 2 in 1, you get PL becomes what? PL max. And I'm sure that you will get VTH square by 4 times RTH. This formula is same for resistor, inductor, resistor, voltage source and current source when the load is, okay? Here also, this is 2, substituting equation 2 in 1, you will get this, okay? So this is the maximum power formula, same you are getting in case of resistor, voltage source, current source when the load is, but the condition for maximum power transfer are changing when the load is changing, okay? So this is very important cases, and the same thing now you are supposed to apply for what? When in case of load, okay, other than these resistor, voltage source, current source are given, then again you are supposed to start from the beginning. Power expressed in terms of only one variable and differentiate that power and make it 0, then you get a condition. That is nothing but condition for maximum power transfer. Substitute that in the power formula, you get the PL max value. That's it. Okay, please note on this. Let me remove this part. Now we will see some problems on maximum power transfer theorem. Question number 17. 17. Find RL for which it receives maximum power. Okay. And also find the maximum power value. He's asking. Both maximum power transfer condition and PL max is expecting. Yes or no? So let us try to solve it. Anyway, for maximum power transfer condition, when the load is resistive element and it is a variable, then you have a formula directly that RL is equal to RTH is the condition for maximum power transfer. Yes or no? Okay. What is the condition for maximum power transfer? RL must be equal to RTH. What is RTH value here in this case? This is suppressed, this is suppressed. Okay. In this example or in this particular problem, there is no dependent source. When there is no dependent source, after suppressing these two energy sources, can we simplify it using normal reduction technique by looking into the network through these two terminals, Nana? Yes or no? Yes, we can do. This is open, this is shorted. When you look into the network through AB terminals, these two are shorted and parallel, and then the result is in series with 3 ohm. Then the result is also in series with what? 2 ohm. So therefore, 6 parallel 12 plus 3 plus 2. 6 parallel 12 is nothing but 4 plus 3 plus 2. 9 ohm. That's it. But to find PL max, you have a formula VTH square by 4 times RTH. That means you definitely need VTH value. Okay. For that, let us remove this load. Let us remove this load. Okay. To find both RTH as well as VTH. Okay. We have to remove the load and let us find VTH. Now this is nothing but, okay, VTH, right? This is VTH. But to simplify with the minimum number of equations, let me not take any variable here, but I'll come back because VTH is nothing but what? Here the drop is 0 because of the open circuit. Whatever the voltage you get at this node, this is nothing but VTH. But to simplify easily, first I take V here, okay? This is V, this is VTH. And these two are in series. There is no need to take any variable. Unnecessarily, let us not waste our valuable time in the simplification. So what will happen? V of 1 by 6, 1 by 12. Don't take 1 by 3 because already current source is there in series with the resistor. When there is a resistor in series with the current source, that should not come in this particular part. Yes or no? Plus 2, 12 by 6. 2 ja. V of, okay, 2 plus 1, 3 by 12 is equal to 4. That's it. So what do you get here? V is equal to 48 by, this is 3 4 ja, that is 4 16 you are getting. That's it. 16 volt. Okay. This is 16 volt, but I would like to get VTH, right? Finally, my objective is to get VTH. So let me jump from this point to this point, and already 2 ampere current is flowing here. So 2 ampere is flowing means what? 3 into 2, 6 volt, but minus plus because the direction is like this. Okay, the current direction will decide the polarities. Now this is VTH, Nana. Jump from this point to this point, then VTH will become, jump from this point to this point. You are jumping from lower to higher, you take the voltage, yes or no? So V plus 16, sorry 6, okay, V plus 6 volts. But already V is a 16, therefore how much it is? 22 volts. Therefore now PL max will become, okay, what is VTH? 22. 22 square by 4 times. What is this value? That's what you're getting here. And you get 13.44 watt. Please cross check once. 13.44 watt. Okay. Note on that quickly. Meanwhile, I just give another problem here. Question number 18. Asked in gate. I read the question. In the circuit shown below, what value of RL maximizes the power delivered to RL? Okay. What value of RL maximizes the power delivered to RL? This is the question. Okay. So now it is a dependent source problem. And what is the question actually here? What value of RL will maximize the power delivered to RL? That means he's trying to vary RL and he wants to get maximum power to RL. Okay. So definitely this problem comes under maximum power transfer theorem. So it is clear that RL is variable. So he's not asking PL max. What is asking? Only condition for maximum power is asking. Yes or no? He is not asking maximum power value. If he is asking maximum power value, you are supposed to find VTH also. Yes or no? But when he is asking only condition for maximum power value, you are supposed to find only RL value. RL is nothing but RTH. Now, only when RTH is required, what is the procedure that you are supposed to follow when there is a dependent source problem? What is the procedure for RTH? Method 1, VOC by ISC. Method 2, Oldham technique. Any method can be followed, no doubt. But what is the best method to find RTH? Okay, only RTH in case of dependent source problem. Obviously, Oldham technique. Okay, so let's go for Oldham technique. Now I am not finding using both the methods. It's a time to judge which one is the best method just by looking at the problem. Okay, so RTH, since RL is equal to RTH is a condition. So RTH using Oldham. For Oldham, you have to suppress all independent energy sources. Yes or no? That's it. Independent energy sources, when you suppress, what will happen, Nana? Okay. This is a dependent source. Okay. We assume it is delivering some current I. This is 4 ohm. This is also 4 ohm. This is also 4 ohm. Yes or no? Minus plus Vx given. Vx is the dependent source upon which dependent variable, it is depending upon dependent variable. Okay. So let us now work out on this. How do you do it? So using again node analysis, if I take this is 0, then obviously this will become V. This is also 0, right? All these are the same. Okay, this is also same. This point and this point both are operating at same potentials. Now you tell me, what do you get? Minus I, node equation, V by 8, yes or no? V by 8, V minus Vx by 4. Now we are supposed to eliminate this Vx, Nana. But what is V actually here? This is the voltage. That means this is the voltage. Between these 2 points, the total voltage is V. And these two are connected in series. Yes or no? Can I divide this voltage between these two? Yes, definitely. So Vx will become 4 by 4 plus 4. Same resistors. Therefore, equal is divided. Okay. Otherwise, you have to apply voltage division rule. Voltage across R1 is nothing but R1 by R1 plus R2 into total voltage. But same. Therefore, Vx will become V by 2. Substitute here and get V is equal to something into I. This something is nothing but RTH. You will get this value. Okay. I can give you the answer here. It must be 4 ohms. Therefore, what is the condition for maximum power transfer? RL is equal to RTH is equal to 4 ohm. That's it. Okay. Note down. Meanwhile, I just give you another problem here. Note down. Question number 19. This one was also asked in GATE. Classroom workbook, question number 19. Hope you have finished that. Yes, if you have finished that, let's come to this problem. It's a very interesting problem. Read the question carefully first. What is the question? In the circuit given below, the value of Kepler required for the transfer of maximum power to the load having a resistance of 3 ohm is. This is a network given. Okay. He wants to vary the resistance here and send maximum power to this 3 ohm. So what could be the value of Kepler is asking. Okay, load is actually 3 ohm and is changing the Kepler value. By varying that Kepler value, okay, he wants to transfer maximum power to the load of 3 ohm. Then for that, what is the value of Kepler? Simply that is the question. Okay, so read that question carefully. Hope you get some answers, right? Okay. Now, whenever maximum power transfer problem is given, or if the problem statement when you read, if you come across maximum power, the term maximum power, don't think that that problem always belongs to maximum power transfer theorem. Or don't think that you always need to apply maximum power transfer condition to that particular problem. It may or may not be. It depends upon the data given. Okay. If you look at this carefully, in this problem, he wants to vary capital R, but he wants to transfer maximum power to 3 ohm. First point to be observed that the load is not variable. Load is a constant one here. When load is constant, what will happen? The problem does not come under maximum power transfer. Yes or no? What is the maximum power transfer theorem actually? Vary the load and transfer maximum power to the load. Here vary some other resistor but send maximum power to the load. So definitely this problem does not come under maximum power transfer. Many of the students in the exam, okay, they did mistakes in this particular problem because after completion of their gate exam, many students shared their views. Okay, some people got the answer something like this. Sir, this is 3 ohm. Therefore, if I put 6 ohm here, 6 parallel 6, 3 and 3, then this is RTH, this is VTH, this is RTH, this is RL. When RL is equal to RTH, then what is the problem? Actually, in that particular problem, in that particular procedure, what are you trying to do? You are trying to get RTH is equal to what? 6 parallel 6, that is 3 ohm. And you are trying to make RTH is equal to RL. You understand? You are trying to make what? RTH is equal to RL. You are trying to vary this R so that the RTH will become RL. Actually, the maximum power transfer condition is not RTH is equal to RL. It is RL is equal to RTH. You understand here? What is the condition? RL is equal to RTH, not RTH is equal to RL. Okay? You may think that, sir, both are same. A is equal to B and B is equal to A, both are same. No. Okay? Here, you need to vary RL, okay, and make it equal to RTH. That's nothing but RL is equal to RTH. The condition for maximum power transfer is you are trying to vary the value of RL until that RL value is becoming RTH. But if you vary RTH, that means you are varying RTH value until it is becoming, equal to RL. So when RL is equal to RTH, then only it is maximum power transfer. But RTH is equal to RL, it is not called maximum power transfer. Understand all of you? Okay, that is not the condition. Okay, so therefore this is completely ruled out. Understand all of you? Then how do you think about it then? See, when the load is constant and some other resistive element is varying and you want to transfer maximum power to the load, this problem does not come under maximum power transfer. But how do you do it? Simple. It is very simple that in whichever the load you want to find the maximum power, you assume some IL. Now tell me what is the PL? Simply IL square into 3. Okay. Now tell me, PL will be maximum, the condition you see here, PL will be maximum when IL is maximum. That's it. Yes or no? Because PL is directly proportional to IL square. Here it is a constant value. Then PL is maximum only when IL is maximum. That's it. Understand? So now let us see. For what value of this capital R, this IL is going to be maximum, so that PL is going to be maximum. Simple. It is as simple as that. So no maximum power transfer condition is applicable here. Now common sense based approach is required here. Understand? Okay. So let us see that. What is it? For what value of this capital R, the current is going to be maximum? You see that IL will be, okay, IL will be 10 volts divided by, what is this? R and 6 ohm, R parallel 6, okay, yes or no? Plus what? 3 ohm. Now suppose if I substitute infinity here, okay, if I substitute infinity here, this is open, then 6 and 3 will be in series. Then in this case, what is the current value? 10 by 6 plus 3, it becomes 9, okay, 10 by 9 ampere. Here, this IL will become 10 by 6 parallel 6, that is 3 plus 3, okay, 6, 10 by 6 ampere. Here, IL will be 10 by 3 parallel 6, that is 2 plus 3, 5, 10 by 5 ampere. Yes or all of you? Okay. So compared to this condition will give you maximum power. Compared to this condition will give you maximum power. But compared to all these three, if you see IL is equal to, if this value is 0, then this entire value will become 0. Then the total current will become what? 10 by 3 only. Okay. Then this particular current is greater than or higher than all these. For what value of R you are getting? 0. Therefore, 0 is the correct answer. I think all of you understand this. Okay. So remember once again, whenever you read the term called maximum power transfer in the problem, don't come to a conclusion that the problem belongs to maximum power transfer theorem. It all depends whether the load is variable or not. Whether you are varying the load and sending the maximum power to the load or not. Okay, if that is not there, then that problem does not come under maximum power transfer theorem. That is why I told you, when I put a title of maximum power transfer theorem, I gave you one important statement that the objective is to transfer maximum power to the load by varying the load. And second point we have written, the load must be variable. And third point we have written, the load might be anything. It might be resistor or voltage source or current source or any other circuit where there is at least one variable. Got it? Please note down this. Okay? Note. Since the load is constant or load is not variable, this problem does not come under maximum power transfer theorem. Simple. So using common sense, that for what value of that R, the current through 3 ohm is going to be maximum according to this particular relation, simple relation you write always. When the problem is not belonging to the maximum power transfer, always try to get this relation. In whichever the element or the load he is expecting the maximum power, first you write the expression of the power for that particular element, you automatically get an idea. Okay? Note down that all of you. I'll go with another question here. Question number 20. It was also asked in GATE. It's a very interesting problem. So let me read it. In the circuit shown below, it is known that, I read it once again. In the circuit shown below, it is known that the variable current source capital I, the variable current source capital I absorbs power. The variable current source capital I absorbs power. Okay. Find I in both magnitude and direction so that it receives maximum power, and also find the amount of power absorbed by it. Hope all of you understand that question. Now here is trying to transfer maximum power to the current source. Okay. and he wants to find that current source value so that it receives maximum power. So that means by varying current source, he's trying to send maximum power to the current source. That means what? Who is acting like a load here in this context? Current source is acting like a load. Case 3 it comes under. Yes or no, all of you? Okay. Unlike the previous problem, he is transferring power to 3 ohm by varying capital R. No maximum power transfer condition is applicable. He is trying to send maximum power to I by varying I. Clear? That's it. But he's asking both magnitude as well as direction. So it is quite easier, right? Look at this. Say this is A, this is B terminals. Okay. If you want to say that it is absorbing power, you want to find the direction of it. Okay. It is possible only when the polarities are known. If I assume this is A, this is B, in circuit analysis, usually AB terminals, A is assumed to be at higher potential with respect to B. So if I assume that A is at higher potential, that means plus, and B is at lower potential, that is minus, definitely to absorb the power, the current direction might be like this only, must be like this only. Yes or no? That's it. So I found the direction. Now I need to find the magnitude of it so that it receives maximum power. Okay. But you know that I is equal to VTH by 2 times RTH. This is what the formula you have. Condition for maximum power transfer. Yes or no? And what is the power maximum value? VTH square by 4 times RTH. That's it. So let us try to find VTH value now. Okay. What is VTH? Let us find. Okay. So all of you redraw the network once again. I'm just trying to do the things here only. Please redraw the network once again. And what is the assumption? Here it is plus, this is minus. This is going to be what? VTH. Okay. Hope all of you understand the question. So that's what I was trying to tell you, that the load may be anything. It might be voltage source, or it might be current source, it might be resistor, or it might be a circuit. It might be circuit. Okay. So what is VTH? How do you find? These two are in series. These two are in series. The total voltage is applied. Say this is V1. Say this is V2. Obviously VTH is equal to what? V1 minus V2. But what is V1? 6 by 6 plus 3 into 24. What is the value? 3 2 ja, 3 3 ja, 3 8 ja, 16 volt. V2. Both are in series. 24. That means 24 by 4 by 4 plus 4 into 24. Okay. That is 2. 20, 12. Okay. So 12 volts. And finally, what is VTH? Touching concept. VTH is equal to V1 minus V2, Nana. Yes or no? 16 minus 12, that is 4 volt. 4 volts. Now RTH will be with respect to AB terminals when it is shorted. Okay, with respect to AB terminals when it is shorted, that means these two are shorted. That means these two are parallel. These two are parallel. Okay, so therefore what do you get? 3 parallel 6, 4 parallel 4, right? And the resulting is in series. So 2 plus 2, 4. Okay. So now what is the condition for maximum power transfer? VTH by 4 times RTH. That means, okay, VTH is nothing but how much? 4 by 2 times RTH. It is also 4, 4, 4 cancel. 0.5 ampere. This is condition for maximum power transfer. What is PL max, Nana? PL max is VTH square, 4 square by 4 times, okay, RTH. What is RTH? Is also 4, therefore 1 watt. This is what PL max. Okay, so this is how you can solve the problem. Okay.